do you fail at your job?
I'm not used to it because
it's not your fault. It's always my fault. What I wanted to say was number 3 is tricky. You need to look up the KBs. Those are conjugate acids. And don't forget that percent ionization or dissociation is X over initial. Okay. I will post this on Schoology. Somebody already asked me to, just in case you didn't finish. You can finish it for homework. Let's learn some buffers. So can you get out your notes? We are here. We actually only have 2 more days of learning for this unit, so we're going to learn buffers today. We'll learn titrations tomorrow. What day is it tomorrow? Wednesday? Thursday, I'm not here. You have some work to do to practice some buffers and titrations. Friday, we'll do a review, and Monday is going to be the quiz. So we'll finish learning tomorrow, Wednesday, and our first assessment will be on Monday. Okay. Before we start talking about pKa, I want to remind us what K means. If something has a big K, that means that the equilibrium lies right. So if the equilibrium lies right, that means that my right side has a lot of stuff. For an acid, that means that my H3O beaker is really full. If my H3O beaker is really full, we call that a strong acid. The more of this, the fuller this is, the stronger the acid. If my K is really small, that means the equilibrium lies left. That means my left side has the stuff and my right side does not have the stuff. So for an acid, if my equilibrium lies left, I have a lot of water and stuff over here, but I just have a teeny drop of the H3O. If I only have a teeny tiny drop of the H3O, we call that a weak acid. Not a lot of acid, very tiny, just a teeny tiny drop of it. Same thing for bases. If I have a really small K, Kb, like times 10 to the negative 10, that means it lies left. That means I only have a teeny tiny drop of my hydroxide. That's a weak base. Okay? P means negative log. So pKa equals negative log of the Ka. I should not have written that right there. So the pKa is the opposite of the Ka because it's the negative log of the Ka. So they're going to be flip-flopped. A big K means a smaller pKa because of that negative sign, which corresponds to a lower pH. That's going to make sense because stronger acids are going to have pHs of like 1 and 2, like lower. If I have a little k, that means I have a big pKa. Big pKa's are going to be, they lie left, so it's a teeny tiny amount. Those are weak acids, so they have a bigger pH, like of 6, because acids stop at 7. Okay? When the music starts, talk about full beakers, less beakers, K, pKa's, and pHs. Ready? Go. Yes, good job. A buffer. The words are a substance that resists change in pH due to the common ion effect. We played common ion before when we did Le Chatelier's with KSP. Like if I add more nitrates, what's going to happen? It's going to shift to the undissolved side. There's two things that have to happen with the buffer. They have to have a common ion, meaning that they've got to have a match, and they have to be similar molarities. Like if they're not the same concentration, really close to the same concentration. That's what makes them work. A buffer works by resisting change in pH. pH equals negative log of the hydrogen. The only way I can change pH is if I increase this or if I decrease that. It's the only thing in the math equation. That's the only thing that's going to change pH. A buffer works because if I add hydroxides, that's a base. Bases produce hydroxides by adding H2O and they lose the hydrogen, gain the hydrogen. If I add an OH, any kind of OH, any kind of base to a buffer, all I'm going to make is water. Water does not change pH. Not because water is neutral, which you might have come to that conclusion, but because water is not in the math. It's H3O, not H2O. If I add an acid, any acid, a Cu, whatever, if I add an acid, all I'm going to make is a weak acid. A weak acid has a very teeny amount of H's. This is like a single drop, right, in the beaker. So it really is only going to change this by like the teeniest amount, which for sig figs does not change the pH. Okay? So it doesn't matter if I add a base or if I add an acid to it, I could add anything to it and the pH doesn't change. So that's what this picture is. This is a common ion. The F is the common ion. This F minus is going to be a basic salt. It's going to be NaOH. They just took out the spectator. If I add OH to it, I'm just making water. Water does not change pH, not because it's neutral, because it's not in the math. If I add a base to it, a basic salt, all I'm doing is creating a weak acid. Weak acids have a single drip drop of the H3O plus, so it's not going to change the pH. Okay? When the music starts, please explain to somebody how buffers work, if I add a base and if I add acid, and why that doesn't change pH. There's the equation for the pH of a buffer. The important thing is it's likely not in the words going to say the word buffer. You have to know it's a buffer because it's going to be a combination of a weak acid and a basic salt, and they have a common ion. Okay. What is the pH of a buffer? Got lucky, it tells us. So now I know what math equation is going to be. That is 0.1 molar in lactic acid. So here's our acid concentration. It's a big, huge thing, but it's a Cu. We know Cu's are weak acids. And 0.1 molar in sodium lactate, a big, huge thing with an Na. That's a basic salt because sodium hydroxide's in the hydroxide group. It gives us the Ka for lactic acid, so we do not have to look it up. pH of a buffer equals the pKa, which is the negative log of the Ka, plus the log of the quantity of the basic salt goes on top. So that's 0.10 over the weak acid. And that's just a regular plain old Cu. Okay, push your buttons because it's not about pushing buttons, it's about being active in your learning. Did you get 3.8? Okay, then with your bad buddy, do number 2. Now you're solving for something different, so it's more of an algebra problem than anything else. Do number 2. Okay, I can't take this anymore.
Stop recording.
Trickiest part of that is doing the order of operations, right? So make sure you do add the log of this to both sides first. Then to undo the log is second log 10 to the negative 0.2, and then just cross multiply. I think it'd be fine if you wrote sodium benzoate instead of actually figuring out what the molecule is. I just take off the H of the Cu and add a sodium. That's all you have to do. On your worksheet, you're going to start at number 23 and stop at 26. 24, 25, and 26 have solution math. So it's like going back to always start with volume. Liters on top means liters on bottom. So a good reminder of how to do that, but that's definitely how it's going to be for quiz and tests and stuff. So 23 to 26, I'll put up answers here in a second. Okay?